Ever wondered how a triangle can capture stress and strain in a solid? Let's break down the constant strain triangle, one matrix at a time. The CST element is a 2D triangular finite element that assumes a constant strain within the element. Each node is represented as a small white sphere. These are the key points where displacement is defined. We will label them node 1, 2, and 3. To describe positions inside the element, we use natural coordinates. From node 1, we draw arrows toward node 2 and node 3 to define the chi and eta directions. These axes help us define shape functions, which map nodal values, like displacement or temperatures, across the element. Let's look at a simple constant strain triangle, or CST, with orthogonal alignment. The nodes are positioned at node 1 at the origin, node 2 at 1, 0, and node 3 at 0, 1. Because of this alignment, the Jacobian is the identity matrix, which means the transformation from local to global coordinates is trivial. We start with the nodal shape functions derivatives. They're constant for linear triangles. Then we map them to global coordinates, which in this case remain unchanged. Finally, we construct the B matrix, which relates nodal displacements to strains. For the same CST element, we can compute shape functions derivatives using the BC method. First, we calculate the area with a simple determinant. Then the B coefficients are the differences in E coordinates, and the C coefficients use the X coordinates. These go directly into the B matrix, scaled by the inverse of twice the area. No need to invert the Jacobian. It's faster, more stable, and especially useful when elements get distorted. That's why the BC method is preferred in many infinite element implementations. Let's walk through a simple plane stress test case using our previous triangular finite element. We're working with a material that has a Young modulus of 200 gigapascals, a Poisson ratio of 0.3, and a thickness of 10 micrometers. A 50 Newton force is applied on the node 2. The area of the triangle has half the determinant of the Jacobian. Next, we define the constitutive matrix for the plane stress condition. This matrix relates the stress and strains in the element and is computed using the given material properties. The element stiffness matrix is calculated using this formula: thickness times area multiplied by the transpose of B times C times B. To compute the displacement at node 2, we reduce the stiffness matrix to the relevant degrees of freedom and apply the external force vector. We are computing strain from the previous CST. The B matrix is built from shape functions derivatives, and the displacement vector is taken from a previous solve. Multiplying B by the displacement vector gives us the strain components for the element. Now we calculate the stress for the computed strain. Using material properties, we build the constructive matrix for plane stress. Then the stress is obtained by multiplying this matrix by the strain vector, resulting in sigma xx, sigma ii, and tau xi values. If you're into FEM, SPH, CFD, remeshing, or just enjoy watching solids get squished by clever math, you're in the right place. I dive into open source solvers, CPU acceleration, and how these methods actually work under the hood. So hit subscribe, or better, hop on the mailing list at opensourcemech.com. No spam, just good stuff. And if you want to support or ask deeper questions, there's always my Patreon. Thanks for watching and happy coding!